So a key topic, obviously, in hydrology is precipitation, and obviously measuring precipitation is pretty important because however the data comes in, that's going to dictate what it is that we can analyze. So you probably have noticed or have rain gauges at your house, or have seen them or heard them discussed on the news and talk about the official rain gauge data versus what was observed at some satellite rain gauge at an elementary school or something like that. So rain gauges, you know, do collect data for single storm events, and how they do that is they use this tipping bucket method. This is a drawing out of a patent for the tipping bucket, for tipping bucket rain gauge. And as you can see there, this huge funnel, not huge, I mean it's about, you know, they're about 10 inches, a foot diameter or something like that, I can't remember how much. It funnels water down into the bucket in the middle there, and this little triangle area is the bucket that I'm referring to here. This triangle area is the bucket, and once the water fills up that bucket, it tips out this way, okay? And inside here there's a little node that records the piece of metal getting hit. Right there, boom, and it makes a little tick, tick, tick. So as it fills up on this side, it'll hit that little green thing, hit a tick, and the gauge records that. And this, right inside here, this volume that we were looking at here is a set volume, so the gauge knows exactly how much rain it takes to fill that up, and then hit the green node there. It's not really green, but I just drew it in that way. And every time it tips back and forth, tip, 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 like this, it records, and so the faster it's going, it starts remembering and recording more intense data. So in a given storm, a rain gauge like this one will record the time, and it'll record the intensity based off of how the measurements are calibrated. So you'll get, you know, a storm event that starts at 3 in the morning. It'll measure the intensity in 0.1 inches an hour and 0.4 inches an hour, and it'll just keep on measuring every so many intervals. It will log what is the intensity over that time slot, and I think that is adjustable, so that by the time your storm is done, you'll have this table of data that represents the whole event. And once you have that data, what you can do is create a graph or a plot of that data, or a bar chart here, where on the x-axis you have time in hours, on the y-axis you have the rainfall intensity, and this is what that data may look like. Now, this data in this format is called a hydrograph. Okay, and from the hydrograph we can calculate the volume of the storm. Actually, we don't need the hydrograph, but from the table we can calculate the volume of the storm. And it's really just the summation of the time times the intensity, right? So hours times inches per hour gets you inches. Okay? So why don't you do that really quick? Why don't you just take a second, find what is the volume of the storm in inches for that event. Okay, so if you haven't found it out already, hit the pause button. But I get 0.75 inches. Nothing too dramatic there, right? Huh? So every 15 minutes or quarter hour you get all of those data. So there you have it. So 0.75 inches. Maybe you get a different number, huh? You can also look at the storm and find out what is the duration of the storm. So this storm happened to last over an hour-and-a-half period. And so if you wanted to know, say, look, maybe we're not concerned about like the hour-and-a-half storm, but what if we wanted to compare this storm to other events of similar time duration? Well, what we need to do is find out what is the volume, given the fact that what would be the volume of this storm if it had lasted 2 hours. So that becomes a ratio problem. So it's very simple there, right? So in other words, you'd get about 1 inch of rain. Nothing very exciting there, but it's sometimes helpful if we want to be able to compare similar storms to each other. Say, well, what is the actual maximum of these two? And because they don't all last exactly the same amount of time, sometimes we will sort of stretch them or shrink them down to a given duration. so that we can compare storms better together. Now, let's say, for instance, you are curious about, we have a gauge that's been sitting there for time, and over time, what do you do with the data? Well, that data, obviously, if you keep a gauge in a place for a year, you can get yearly water volume at that gauge. That's when you get, the basic statistics you can find on Wikipedia saying, how much rainfall does Los Angeles get? Well, you Wikipedia that, and you'll find out that LA basin gets something like 13.5 inches. That means that over the course of a given year, that is the total volume of water that has been recorded at a specific gauge. You can also aggregate that into monthly data if you're curious how much of the water comes during January, February, March, or April, May, so that sort of thing. The other thing we do too is if we have a gauge that's recording individual storm events, we will sometimes just pull out what was the maximum event for that given calendar year. And what that gives us is this thing called the annual maximum series, and that's what we use in what is required to be used anyway in Bulletin 17B to do the extreme value analysis. So if we want to know if our goal is to find out what is the most extreme storm that we might expect for a given region and what storm event do we want to protect ourselves against, we need to go back through the historical data and pull out those maximum storms in any given year, and we use that to do the statistical analysis. It might be also that we have multiple storms being observed over multiple gauges. In other words, we have multiple gauges running and recording data, and that allows us to get sort of the spatial distribution of our precipitation. And that's helpful because now we can create maps of our precipitation. We can demonstrate that if you're in this location, this is probably what your precipitation will be, rather than saying, well, LA has 13 inches of rain or whatever, and I guess that applies to our site that's in Pasadena, which it doesn't. So we put up multiple gauges and then we can create these maps, and here's an example of those maps. This map is called a depth duration frequency map, and you can see on there all these black lines, and this map comes from Riverside, California, or Riverside County in California. All those black lines there, and let me highlight some. This is saying that this is the 100-year 24-hour duration storm. And the black line that I'm highlighting there is called an isoheat. What it means is that line represents the same precipitation depth. So that line is a precipitation depth that's defined on the map there. You can notice that the contour, these lines look a lot like contours, and they're the same concept, just that contours are for elevation as isoheats are for rainfall depth. So that's the kind of data that we can get out of this, is that we can analyze these gauges and expand or contract those storms to see how they would fit to a 24-hour distribution, how much rain would have fallen in 24 hours, and then analyze them based off of what would be the 100-year storm event. So it's very common to use the 24-hour storm throughout the country as the main design storm. It is less common in the desert Southwest because there the most extreme storms we get are fairly short duration. But in general throughout the U.S., most people design off the 24-hour storm. So let's say this little orange blob represents the watershed that you're working in. And that little dot in the middle is the centroid. For a depth duration frequency map, one of the easiest ways to grab the data from it is to mark down the centroid and read the depth from the centroid of the basin. There are better ways than doing this, and they involve software. They involve GIS and mapping software, and they require the precipitation depth duration frequency map to be digitized as well and turned into like a DEM of some sort. So there are better ways of doing this. They involve software, and they involve a pretty decent knowledge of ArcMap functionality. So usually you don't have to work with this data, but unless you know that software, otherwise we'll continue working with it. One of the other common forms of data, that we get are graphs that look like this. This is an intensity, duration, frequency curve. And you can see here what I mean by that is, we got duration and frequency, duration on the x-axis, intensity on the y-axis. The duration, these charts are used in the rational method. And when we talk about duration for the rational method, what we're talking about is the time of concentration. So it is your job using this graph to find the intensity of the storm, and that's what's the key, one of the key terms in the rational method, as we'll discuss later. But finding the intensity from this graph is usually objective. So the first thing you do is you select or identify your risk level that you're willing to accept. So maybe you're designing your storm for the 50-year flood, or you're designing a culvert for the 100-year flood. Whatever it is, you need to know that walking into this figure. As you can see, there are multiple lines that correspond to the 2, 5, 10, and so on to the 100-year. The second thing you want to do is calculate the time of concentration for your watershed. So once you have the time of concentration, then you can use that to look up the intensity from the IDF curve. So let's do a quick example of this procedure here. So let's say you are given that we want to find the rainfall intensity for the 50-year storm, and we're given a time of concentration of 45 minutes. Well, this 45 minutes is looked up down there on the x-axis of this IDF curve, and we draw a line up to where it intersects with the 50-year curve, and then draw a line to the left over to read off the intensity. So those are our units, inches per hour, so therefore our intensity for the 50-year storm is 3.5 inches per hour. It's very, very simple to do. So you got to be careful here. All right? This figure cannot be used everywhere. All right? I don't know if you noticed the top of this figure, but it is based off of data from Baltimore, Maryland, and it's based off of data, which is very handy for them to list this, from 1903 to 1951. That was what created this data. So they did the extreme value analysis on this data. And you can also notice there that the extreme value data that we have, it says here, is after Gumbel. So they didn't use Bulletin 17B to analyze this and get this data, which is fine. They're free to do that. But you cannot just grab an IDF curve from, let's say, Orange County and use it in Riverside County. You can't take precipitation depth maps, depth, duration, frequency maps from King County, Washington, and apply them to Maricopa County, Arizona. So everywhere you go, they have this data, and it is defined. It's pretty specific as to when you can use it, where you can use it. So you can't just piece together information. Now, there are some counties and some regions that don't have this data defined, in which case you can just go back and rely on national data sets. And what do I mean by national data sets? Well, one of the national data sets that is most common is the NOAA Atlas 14. You can Google that and go to their website. NOAA Atlas 14 has a very nice interactive map for several of the states in the United States, and it provides you with DDF maps if you want, or you can also use the DDF maps where you zoom into a specific location and have it give you the IDF curves for your site. So NOAA Atlas 14 is very, very nicely done. It's just that some localities like Southern California specifically do not allow you to use NOAA Atlas 14, but it's kind of funny because they base most of their precipitation data off of their analyses. So, but excuse me, most of the United States uses NOAA Atlas 14, but then they tweak it for their own local or regional needs, if that makes sense. But like I said, you can just Google that data, go to their maps, and then kind of walk your way through the website to figure out where are the depth, duration, frequency maps, or where are the IDF curves for your given site. So that's our brief overview of precipitation data.